Hello everyone, here you are once again going to watch one of the miracle engineering examples of the Victorian era. I think you already know this structure. Perhaps you pass in front of it at every opportunity or even use it. In 1886, the Corporation of London approved the construction of a bascule bridge over the River Thames near the Tower of London. The bridge was designed to open 8,000 times a year to allow tall-masted ships to pass to the Upper Pool wharves. Engineers specified foundations driven 70 feet down into the clay beneath the riverbed, bascule chambers of wrought iron weighing more than 1,000 tons each, and hydraulic accumulators sized to enable uninterrupted operation throughout the day. The design was based on the assumption that ship traffic would increase indefinitely. Within 30 years of the bridge's completion in 1894, deep water ports further down the river had captured almost all cargo traffic. The Upper Pool emptied. Ships stopped coming. Today, 130 years later, Tower Bridge opens fewer than 1,000 times a year, and very interestingly, still does so using the same hydraulic machinery installed in 1894. The bridge built for ships that would never come outlived the maritime industry it was intended to serve. While watching this video, don't forget to press the subscribe button below. By doing so, you are not only supporting the production of more content like this. A simple subscription shows us that these words have reached you, that the story of Victorian engineers who built for impossible futures means something to someone on the other side of the screen. So, like the video and subscribe to the channel. The problem Tower Bridge solved in 1886 was real. The Pool of London had been the city's main port for centuries. By the 1880s, ships had grown larger and taller. Their masts and rigging could no longer pass beneath the fixed London Bridge. Cargo ships faced a choice: unload below London Bridge and transfer goods by smaller boats, or proceed to ports downriver and accept higher transport costs to central London. Neither was efficient. The Port of London authorities needed a bridge that could carry road traffic yet open frequently for ships. The Bridge Committee held a competition in 1876. Nearly 50 entrants submitted designs, but none were accepted. The committee reopened applications, and eventually, in 1884, engineer John Wolfe Barry and architect Horace Jones submitted a bascule design and won. Barry and Jones proposed twin towers built upon massive foundations and two counterweighted bascule leaves that could be raised in 90 seconds. The design was unprecedented in scale. Bascule bridges existed at the time, but none approached the dimensions of Tower Bridge. Each bascule leaf would weigh more than 1,000 tons. The towers would rise 213 feet above the Thames. Foundations would extend 70 feet below the riverbed. Hydraulic machinery would operate continuously every day. Critics argued that simpler designs, such as a swing bridge or a high-level fixed bridge, would be cheaper and require less maintenance. Barry insisted that only a bascule design could provide the necessary clearance while minimizing road closure time. The corporation accepted his argument, and construction began in 1886. The engineering and labor challenges became apparent immediately. At the bridge site, the Thames riverbed consisted of 40 feet of soft clay and alluvium over gravel and sand. Stable London clay lay 70 feet below the riverbed. Barry determined that the tower foundations needed to reach this clay layer to prevent settlement. Contractors built watertight cofferdams around each tower foundation and worked inside them after draining the water. Workers excavated riverbed sediment by hand, removing material in buckets lifted by steam cranes. The excavations continuously filled with leaking groundwater. Pumps ran without interruption to keep the working area dry. Once solid ground was reached, workers poured mass concrete foundations 70 feet deep and 50 feet square. Concrete was mixed on barges and poured during continuous operations lasting days. Each foundation consumed more than 6,000 cubic meters of concrete. The towers themselves were built as steel frames clad in granite and Portland stone. The steel provided structural strength. The stone gave the structure its Victorian Gothic appearance and protected the steel from the Thames atmosphere. Each tower weighed more than 11,000 tons. Stonework alone exceeded 6,000 tons per tower. Granite came from Cornwall, while Portland stone came from Dorset. Every stone block was cut to size, numbered, transported by rail and barge, and positioned using steam cranes. Progress was slow. Weather frequently halted construction. Labor strikes caused delays. Accidents were common. Several workers fell from scaffolding and drowned in the Thames. Completing the towers took 5 years. The bascule mechanism was the most complex element of the project. Each leaf consisted of a lattice girder structure weighing 1,070 tons. The leaf was balanced by a counterweight of concrete and iron located in the bascule chamber beneath the bridge deck. The counterweight was calculated so precisely that when the leaf rose, it remained in perfect balance, requiring minimal force to hold it open. The pivot mechanism used a massive horizontal shaft, 12 inches in diameter, supported on roller bearings. The entire system was designed to operate thousands of times annually without failure. Engineers chose hydraulic power over steam or manual operation because hydraulic systems offered precise control and could be operated remotely. The hydraulic system was designed from start to finish with conservative safety margins. 6 large vertical cylinders, accumulators containing iron-weighted pistons, stored hydraulic pressure generated by steam-driven pumps. The accumulators were designed with enough capacity to open the bridge 10 times without running the pumps. In practice, the bridge rarely opened more than 4 times before the accumulators needed recharging. Hydraulic pipes were made of wrought iron and sized to withstand pressures far above working loads. The entire system assumed the bridge would open at least 20 times daily, more than 7,000 times a year. Engineers expected maritime traffic in the Upper Pool to continue growing as London's population increased. Construction was completed in 1894. The Prince of Wales opened the bridge in June. The ceremony attracted thousands who watched the bascule leaves open and close repeatedly as a demonstration. Toll collection began immediately. Pedestrians crossed free while vehicles paid according to type and load. Bridge operators recorded every opening in detail, noting date, time, ship name, and duration. These records documented the bridge's operational life and revealed a pattern the engineers had not foreseen. In 1894, the bridge opened approximately 6,000 times. This met expectations. The Upper Pool wharves were busy with cargo traffic. Ships queued to pass through the opened bridge. Hydraulic machinery operated smoothly. The bascule leaves opened and closed without issue. Everything worked as designed. But the maritime order was already changing. Sailing ships were being replaced by steamships. Steam-powered vessels required deep water and long quays for coal loading. The Upper Pool wharves could not meet these requirements. Shipping companies invested in new downstream ports at Tilbury, where the Thames widened and deepened. These ports offered modern cranes, railway connections, and space for large ships. Upper Pool traffic began declining almost immediately. By 1900, bridge openings had fallen to 5,200 per year. By 1910, the number was 3,800. In 1920, it dropped below 2,500. The decline continued throughout the 20th century as the Upper Pool shifted from freight transport to passenger and tourism traffic. Wharves closed or were converted to other uses. Tall-masted ships disappeared. Bridge operators found themselves running a mechanism designed for 8,000 operations annually, yet used fewer than 2,000 times. The machinery sat idle for most of the day. Accumulators maintained pressure for openings that never occurred. Counterweights balanced bascule leaves that rarely moved. The bridge's survival despite declining use proved the value of over-engineering. The hydraulic system designed for continuous operation experienced very little wear due to lower usage frequency. Bascule bearings sized for heavy daily cycles showed minimal deterioration even after decades. Wrought iron pipes and cylinders built with generous safety margins operated far below stress limits. Machinery that seemed excessive in 1920 became critical when London began preserving the bridge as a historic monument in 1950. Had the system been built to minimum requirements for 1894 loads, it would have needed replacement before 1940. Thanks to generous engineering margins, the original 1894 machinery could continue operating indefinitely. Over 130 years, various modifications were made, but the core mechanism remained unchanged. Steam engines driving the hydraulic pumps were replaced by electric motors in 1976. Original accumulators were preserved and refurbished. Bascule pivot bearings were inspected and found in excellent condition, despite 130 years of use. Modern computer controls were added to automate openings, but the hydraulic cylinders, pipes, and bascule leaves remained exactly as originally built. The bridge, designed to open 8,000 times annually, now opens about 850 times a year, serving tourist boats, ceremonial events, and the occasional tall-masted vessel instead of the cargo traffic envisioned in 1894. By 1930, Tower Bridge's economic justification appeared weak. Critics argued that the bridge was an expensive mistake, built for shipping traffic that shifted downstream before construction even finished. Capital costs exceeded £1.1 million, annual maintenance cost thousands of pounds, tolls never covered operating expenses. The Corporation of London subsidised the bridge from its general budget. A cheaper fixed bridge or tunnel might have handled road traffic without the complex bascule mechanism. These criticisms were narrowly correct, yet they missed the broader point. Tower Bridge was not built solely for the maritime system of 1894. It was built to enable future possibilities that engineers could not define. The decision to design for 8,000 openings annually, far more than observed traffic, created a structure capable of serving purposes not yet known. When cargo ships stopped coming, tourist vessels appeared. When steam gave way to diesel and sail became recreational, the bridge adapted. Generous engineering margins allowed the structure to serve uses its designers never imagined. A bridge built to minimum specifications would have required replacement once maritime patterns changed. Tower Bridge's excess capacity became its greatest advantage. The survival of the 1894 hydraulic machinery illustrates principles extending beyond bridges. The same mindset that designed accumulators capable of 10 openings when 4 would suffice also produced 6-foot-thick coastal walls, 4-foot-thick factory walls, and sewer tunnels 3 feet in diameter. Victorian engineers consistently overbuilt because they understood that infrastructure could not easily be replaced, and future demands were unpredictable. Tower Bridge embodies this philosophy in a structure that remains indispensable 130 years after its original purpose largely vanished. The comparison with modern infrastructure is instructive. Today's bridges are often designed with precise optimization for expected loads over specific lifespans of 60 to 70 years. Materials are selected for minimum adequate strength. Safety factors are calculated according to standards. Maintenance is planned around anticipated deterioration rates. These approaches produce efficient structures under known conditions. Yet they fail when conditions change. A bridge designed for a specific traffic pattern becomes obsolete when that pattern shifts. Renewal becomes necessary, not because the structure fails, but because it cannot adapt. Tower Bridge was designed for conditions that never fully materialized, yet it adapted to conditions its builders could not foresee. The mechanism built for cargo ships now serves heritage tourism. The hydraulic system designed for 8,000 openings annually operates at 1/8 that frequency with almost no wear. Foundations that once seemed excessive continue supporting a structure whose use has completely transformed. This adaptability was not planned. It emerged from engineering built far beyond immediate necessity. The human cost of Tower Bridge was significant. Construction employed more than 400 workers over 8 years. 5 workers died during construction, 4 from falls, 1 crushed by machinery. Hundreds were injured due to scaffold collapses, crane accidents, and exposure to Thames water. Workers excavating 70 feet into riverbed clay labored in darkness and cold, at risk of drowning if cofferdams failed. Stonemasons placing granite cladding worked at heights exceeding 200 feet with minimal safety equipment. The engineers designed the bridge through calculations and drawings, but workers built it with their bodies. John Wolfe Barry died in 1918. Horace Jones died in 1887. Before construction was completed, neither lived to see the maritime decline that invalidated their traffic projections. Yet they built knowing that the bridge needed to outlast maritime systems, economic cycles, and technological change. Tower Bridge remains in daily use today. Road traffic passes continuously. The bascule leaves open about 850 times a year, scheduled weeks in advance to minimize disruption. Victorian hydraulic machinery. though controlled by modern computers, still functions exactly as designed with 1894 components. The bridge, once considered excessive, now sits at the center of London's identity, a working monument to engineering that refused to accept good enough when permanence was required. The ships it was built to serve never truly came, but the structure built to serve them endures.